Hello, let's talk about electromagnetism. So first thing we're going to start with is straight magnetism and magnetic field lines. So every magnet has a north pole and a south pole, sometimes in far more complicated arrangements than this. Your standard bar magnet is the easiest example, and so we'll go over that one. It comes up a lot in the questions as well. So with your standard bar magnet, you've got a north pole, which is kind of like a charge, like positive or negative. We just happen to call it north, and we call the opposite charge south. So there's no real relation with like geographical north, like the direction north, except for one which we'll get into later. I just think of it as like positive and negative for magnets. So here's what the magnetic field lines look like for a bar magnet. You got the field lines coming out of the north charge and going into the south charge. Be pretty familiar with this. Out of north towards south, that's always the way of things. So getting back to the whole why we call it north and south, we've known about magnetism for a really, really long time. And people notice that any magnet, if you held it very still, say put it on a string really well, the north charge of the magnet would point towards the north pole. So the Earth rotates on its axis, and at one point where the axis intersects the Earth's surface, we call that the North Pole. And in the other place where the axis of rotation intersects the surface, we call that the South Pole. So that's the geographic North Pole or the geographic South Pole. That has to do with the Earth spinning. But the Earth is also a giant magnet. And so, confusingly, but it makes sense in how they named it, really close to the geographic North Pole, there's a magnetic pole of the Earth, but it is a south charge magnetic pole right there. And so you can imagine any magnet on Earth, the north side of it will be attracted to the south charge of the Earth, and the south side of a magnet will be attracted to the north charge of the Earth. So at the north geographic pole, there is a south magnetic pole, more or less. It's actually staggered by a bit and moves, confusingly. It used to be in Canada, it's heading towards Russia right now. Slowly, but faster than we would think. Anyway, so people named the two sides of the magnet, the two charges, north and south, because all north magnets, or north sides of magnets, seem to point towards the North Pole, and all south sides of magnets seem to point towards the South Pole, and that's because the Earth is a big magnet, though it gets a little confusing. Anyway, now this little bit's pretty interesting. So the laws of electrostatics are very, very similar, especially once you get into university and get to Maxwell's equations. You'll be like, there is a lot of symmetry here between electricity and magnetism. Really, if we could find like something with a single north charge and no south, or a single south charge and no north, it's called a magnetic monopole. Just because we can find with electrostatics, you got a positively charged particle or a negatively charged particle. If we could find that, they would be perfectly symmetrical. Your equations for magnetism would perfectly match the equations for electrical objects. But we've never discovered it. If you take a north-south magnet and you chop it in half, you just end up with two north-south magnets. You don't end up with a north side and a south side. And that's no matter what. Even, you'll find out later that even subatomic particles like electrons have their own little magnetic field, and they have their own north side and their own south side. They have a property called intrinsic magnetic moment that determines the amount of charge, and they can line up their direction. All right, so let's talk magnetic field lines. Magnetic field lines, again, always go from north to south. So what do you think would be the right answer? Which has field lines just going from north to south? Does this look right? That doesn't seem to be going from north to south. What about this guy? Again, not really going north to south and not north to south. This one, again, doesn't look right. We should be having field lines going north to south, though the north to north looks fine. You got no field lines going between them. So the just right one is B. You've got magnetic field lines going from a north pole to a south pole, but they kind of bend from north to north, just like we saw with electrostatics with repulsion, if we had a negative and a negative or a positive and a positive. Again, the field lines look very similar to electrostatics, except we always have a north charge and a south charge. And think of them as charges again, because it gets confusing with north the direction and north the charge. I really think they should come up with a different name, but it was named long, long ago. All right, that's it for now. I'll talk to you later.